Okay, in this video we're going to continue exploring how to solve second order linear differential equations that are homogeneous and constant coefficient like this, and the connection between that and the corresponding system. So we know that we're going to go to the characteristic equation, which is just as squared plus bs plus c equals 0. Corresponding characteristic equation over here, same equation, we're just using lambda as our variable when we're solving for eigenvalues, and s is our variable when we're solving a second order differential equation. All right, and you don't have to. I mean, if you wanted to use lambda here, you could. I'm just following the conventional notation from the textbook. Okay, so I want to look at case 2 where we have two complex roots. So s equals alpha plus or minus beta I, which would mean here that lambda would equal alpha plus or minus beta I. Okay. So what I'm going to do is pick one of them. I'm going to pick S1 equals alpha plus beta I. And then I know that y sub c, now I'm just putting a c there to indicate that this is a complex solution to this real differential equation. Not necessary to do that, but I want to reserve the name y for my general real valued solution. So I'm going to call this one y sub c. So this would be e to the alpha plus beta I times t, which I can simplify. E to the alpha t times e to the beta I t. And then, of course, I can use Euler's formula for this. So that's going to be e to the alpha t times cosine of beta t plus I times sine of beta t. Now, if I distribute the e to the alpha t, that's e to the alpha t times cosine of beta t plus I times e to the alpha t sine of beta t. So, this is the real part of y sub c, and this, not including the I, just the real valued function that gets multiplied by I, is the imaginary part of y sub c. I could actually confirm directly by just plugging into the differential equation and using the fact that this was a root of that characteristic equation, that this and this are both solutions to the original differential equation. And it does turn out that the general solution is just going to be an arbitrary linear combination of the real and the imaginary parts of that complex solution. So that's very, very nice. And in general, I'm not going to need to pass to the system in order to see that. I want to just take a look at the system so that we can see how that does work out, and again, really understand the connection between them. So over here, if I were to form a complex solution, again, I'm going to just put a subscript of c to indicate that this is my complex solution. It would be e to the alpha plus beta I times t times v, and I'm going to put a subscript of c, okay, where v sub c is a complex eigenvector for alpha plus beta I. Okay. So I know that's going to be e to the alpha t times e to the beta I t times v sub c, which is e to the alpha t times cosine of beta t plus I times sine of beta t times my vector v sub c. Okay. Now, I don't have a specific example, so I haven't actually formed a specific eigenvector here. But if I were to do that, I can see that what I'm going to get in my vector valued solution is I'm going to have that y sub c is going to consist of e to the alpha t times some sines and some cosines of beta t. How many sines and cosines I get here is going to depend on exactly what this eigenvector is. But I'm going to have, let's see, what letters do I want to use? I'm just going to say a copies of sine beta t plus, I'm going to skip B because it looks like beta, plus C copies of cosine beta t, plus then I copies of e to the alpha t times d copies of sine beta t plus e copies of cosine beta t. Now, the values of A, C, D, and E will be determined by what these coefficients, what the components of this complex eigenvector are. And probably some of them are going to be zero. It's entirely possible that here I have some sines but not some cosines, or vice versa. But I'm always going to get e to the alpha t times some sines plus some cosines, and then I times e to the alpha t times some sines plus some cosines. And I'll have something similar here for the second component. I'm not going to bother to write that out because I'm really just concerned with looking at how this translates back to the solutions that I have over here. Okay. So, if that's my complex solution, here's the real part, and here's the imaginary part for just the y that we would get. So a complex solution for y would just be this. I'm not going to bother to well, actually I will. Okay, so e to the alpha t times a sine beta t plus c cosine beta t plus I times e to the alpha t times d sine beta t plus e cosine of beta t. Okay. Now, this solution doesn't look quite as simple as this complex solution that we had right here, where I had just one copy of cosine and one copy of sine. Okay, so this complex solution may or may not correspond exactly to what we get right here. But if I look at the real part of this and the imaginary part of this, which doesn't include the i's, and I were to say, okay, I can then build my general real valued solution by taking some of these and some of those. Okay, so k copies of, I'm just going to write y sub c real and y sub c imaginary here, keeping in mind that this complex solution is not necessarily exactly the same as this complex solution. They're both complex solutions for y, but not necessarily the same. These are two different ways of working out the problems. So I would have k times k copies of this real part plus, I'll say k1 and k2 copies of this imaginary part. Okay. But what that's going to amount to is I've got some copies of e to the alpha t times some sines and some cosines, plus some copies of e to the alpha t times some sines and some cosines. If I consolidate, I can say that's some copies, I'm going to switch to capital letters, k1 copies of e to the alpha t times some sines of beta t, plus capital K2 copies of e to the alpha t times sine of beta t. All I've done here is I've said let K1 be the total number of copies of e to the alpha t times sine of beta t that I have. I'm going to have some sines here and maybe some sines here. Just consolidate them. That's how many copies I have. I'm going to have maybe some cosines here and some cosines here. Just consolidate them, and that's how many, whoops, I wrote sine twice. And that's how many sines I have. So over here, If I were to just take some copies of the real part and some copies of the imaginary part, K1 copies of the real part of this complex solution that I have over on this side of the board, plus K2 copies of the imaginary part, that would just be K1 copies of e to the alpha t times, I should switch it because I wrote signs first here. So let's take K2 copies of this and K1 copies of this. I'm just trying to make it so that K1 is the coefficient in front of sign. So I need to have K1 copies of this part that has the signs in it. Okay, so I would have K2 copies of e to the alpha t times cosine of beta t plus K1 copies of e to the alpha t times sine of beta t. So I do end up getting the same general solution for the real valued function. So this is my general real valued solution Okay, so it's a whole lot more complicated actually to solve the system here, because we sort of have to figure out how many sines and how many cosines are part of the real part, and how many sines and how many cosines are part of the imaginary part. Much simpler to just work over here, but I wanted to show you, first of all, that we do get the same answer either way, and second of all, that if you do choose to work things out, it may not necessarily be that the real part of the complex solution that you have here, which involves one copy of e to the alpha t times cosine of beta t, corresponds to the real part over here, where you might have some other copies of sines and cosines, but that when you put the pieces together, all you're going to get is e to the alpha t times some sines plus e to the alpha t times some cosines. We'll do an example in the next one.